Before starting any standardization or inspection with the phased array instrument, it is essential to perform the element verification. This test allows us to ensure that all transducer elements are functioning correctly. The instrument activates each element individually and displays a map or chart showing the response of each one. If any element appears weak or shows no signal, it can affect the beam focusing and the overall image quality. For this reason, it is always necessary to verify that all elements are active before continuing with the setup or scanning process. To begin the adjustment, we enter the application menu and select the probe test option. Within this configuration, we select the transducer being used. This is done through the option located in the upper left area of the screen. Here we must select the transducer, and the instrument will automatically display its configuration. In some cases, the instrument recognizes the transducer automatically. If not, it must be selected manually according to its specifications. Next, we set a thickness of 25 millimeters, corresponding to the reference block to be used. In this guide, we will work with an IIW block. Then, we adjust the material velocity and the wave mode. Making sure the value is 5,800 meters per second, which corresponds to the material type of the block being used. We press the Calculate key so that the parameters are applied to all elements. Now we press the next key to display the other parameters to be adjusted. Once the transducer has been modified, we can observe its updated configuration in the lower left area of the screen. This adjustment allows us to control the active aperture of the transducer, the beam focusing, and to avoid using damaged elements. By defining the correct range, the instrument will form the beam accurately, ensuring a more reliable inspection. In this example, we will start with element 1 and end with element 16. We change the range value to observe the backwall echoes of the material thickness, along with the multiples of the first echo, by setting a value of 100 millimeters. According to the type of transducer, we set the voltage to 20 volts. The voltage regulates the energy of the ultrasonic beam, achieving the best balance between sensitivity and resolution depending on the material, thickness, and type of inspection. Next, we configure the PRF, which controls the number of pulses the instrument sends per second. A high PRF improves the image refresh rate, although it may generate false echoes. For this reason, it is important to adjust it correctly to obtain a stable and accurate signal. We select the Auto Rec option and calculate the values again to apply them to all elements. Now we press the next key. In the next configuration, we set the amplitude reference value to 80%. With a tolerance of plus or minus 2 decibels. We press the next key. At this point, we couple the transducer without the wedge to the IIW block. We apply a small amount of couplant to the surface of the block and couple the transducer. If necessary, we increase the gain until an amplitude of 80% is obtained on the vertical scale. We can now adjust the gate to intercept the thickness indication coming from the back wall. As we can now see on the screen. Once we confirm on the screen that all elements are within the amplitude range and tolerance, we press the scan key. At this step, the instrument generates a report for each element, indicating whether it is functional or non-functional. By pressing the report key, we can enter the transducer data as well as the reference block used. By pressing the OK key, the system generates a report in PDF format, which can be attached to the inspection documentation. Finally, we press the back key to return to the main screen. And select Finish to complete the verification. Wedge verification. Before performing standardization on a phased array instrument, it is essential to verify the wedge. This verification ensures that all transducer elements are functioning correctly and that ultrasonic transmission is accurate. The first parameter to be verified is the first element height. The first element height determines the point where the wave originates on the surface. This value directly influences beam focusing and inspection accuracy. Incidence angle. The incidence angle is the angle at which the ultrasonic wave enters the test piece. It is important because it defines how the wave refracts within the material. Refraction angle. Finally, the refraction angle is the angle adopted by the wave once it is inside the material and determines the beam path toward the area to be inspected. For this initial setup, with the wedge not installed on the transducer, we enter the main menu and select Wedge Cal. The instrument includes a list of predefined wedges, but if the model is not listed, it must be added manually along with its manufacturing parameters. We select the wedge and confirm by pressing the OK key. We can verify in the upper left area that the correct transducer has been selected. Next, we adjust the following parameters. Reference 25 millimeters. Probe delay 0 microseconds. Material velocity 5,920 meters per second. Delay 0 millimeters. This is configuration 1 of 3. Configuration 2 of 3. We adjust the range to visualize 2 to 3 echoes, setting an approximate value of 100 millimeters. The gate must touch the first echo and cover the entire screen. With a height of 20%. In measurement mode, we will use the peak option. Next, we calculate the pulse width using the mathematical formula, 500 divided by the frequency. The pulse width represents the duration of the ultrasonic signal emitted by the transducer. A short pulse improves resolution, making it ideal for detecting small and closely spaced defects. A longer pulse improves penetration, which is useful in thick materials, although it reduces resolution. In summary, it is calculated to achieve a balance between resolution and penetration. For this transducer, we will use a pulse width of 125 nanoseconds. Now we will perform configuration 3 of 3. We will begin by verifying that the voltage is set to 20 volts. TX energy controls the amount of energy sent to the transducer. Increasing the energy provides greater penetration but lower resolution. Reducing it improves resolution but decreases range. For this example, we will use a value of 1. The wave rectification will be full wave. The simple number parameter defines the amount of data captured by each active channel. For example, with 16 elements by 16 elements, we use a value of 256. Adjusting these parameters can improve the signal-to-noise ratio, and the ideal value will depend on the transducer model. We return to configuration 1 of 3, and it is time to apply couplant to the block as well as to the transducer. We increase the amplitude using the auto 80% function and press the zero calibration function button. Once the zero calibration has been completed, we apply it to all elements using the calculate function. It is now time to install the wedge onto the transducer. We install the wedge on the transducer, ensuring proper coupling, and verify the previous configurations. The pulse width and the voltage, the transmission energy, rectification, and the number of electronic elements. Now we press the next button and change the range to visualize the reference echoes coming from the transducer. We also change the velocity to 3,220 meters per second, corresponding to the material of our block. We also move the gate so that it covers from the first element to the last. Once we ensure that the gate detects all elements, we press the calibration key. At this point, the wedge has been verified. We press the finish key, and the instrument prompts us to confirm whether we want to save the changes. Once the changes are validated, we can view the configuration of the new wedge and further customize the information with greater precision. We've concluded the wedge verification. The following parameter configuration is based on the characteristics of the transducer and the inspection conditions. As a first step in the main menu, we navigate to the Transmit option. In this menu, we find the transmission parameters. The current level is automatically set to 1, which represents a low energy level, ideal for initiating the setup. The next adjustment is the pulse width, which, according to the formula 500 divided by the frequency, results in 125 nanoseconds for a 4 MHz transducer. The voltage is set to 20 volts. TX energy set to 1. And the PRF set to automatic mode, auto rec. Next, we press the Receive key and select the transducer bandwidth or its center frequency. In this case, it is 4 MHz, so we select the range in which this transducer falls. There is a parameter known as dynamic gain. In a sectorial scan, each angle or focal law travels a different distance within the material. This causes the echoes to have different amplitudes. For example, higher angles, such as 70 degrees, usually produce weaker signals than 45 or 60 degrees. Dynamic gain corrects this difference by applying automatic gain to each angle. In other words, the instrument compensates for amplitude variations and keeps all signals at the same level, regardless of the angle of incidence. However, for this example, the gain we will use is known as analog gain, and the value will be 30 decibels. The next parameter is compensation. Its main function is to compensate for energy loss with depth. As the ultrasonic wave travels through the material, its energy decreases, causing deeper signals to appear weaker. It also allows the instrument to progressively increase gain, maintaining a uniform amplitude across all echoes. This is very similar to TGC, time gain compensation, but in a more automatic and controlled manner. For this example, we will leave compensation at 0 decibels. In summary, dynamic gain corrects amplitude differences between angles, while compensation offsets energy loss due to depth or distance. Together, they help obtain a more uniform sectorial image, with balanced signals and improved interpretation of indications within the weld. For the next parameter, wave rectification, we select full. Under sampling elements, simple number, we keep the value at 256 elements. Finally, we have the sampling frequency. This setting defines the quality and accuracy of the signal recorded by the instrument during the inspection. When the transducer receives the ultrasonic signal, the instrument converts it from analog to digital, and the sampling frequency indicates how many times per second the system takes a sample to reconstruct that signal. For this example, we select 100 MHz. We have concluded the ultrasonic setup. Test piece configuration. Scan plan. In the instrument's main menu, we select the Scan Wiz or App option. Both options allow you to create a scan plan, but the App option provides a more comprehensive configuration. We select Flat Weld and press Next to design a new plan. In this case, we will work with a single group. And select the material velocity again. Next, we enter the thickness of the component to be inspected. For this example, the component thickness is 3/4 of an inch. These initial settings correspond to step 1 of 1. We then press 2 of 2 to continue and select the Add option. The instrument will display a screen showing the available weld geometries. We select the corresponding profile, which opens a new window with several configuration options. We then select the V-weld type. From here, we can begin configuring the weld profile. In the first field, we enter the base material thickness, excluding reinforcement, 3/4 of an inch. Under MT type, we select the material type and verify the longitudinal and shear wave velocities. Next, we define the weld parameters. The W parameter corresponds to the width of the top reinforcement. For this example, we will use a value of 0.900. Root D is the width of the bottom reinforcement. We will set a value of 0.250 inches. The UHT parameter corresponds to the height of the top reinforcement. We will set a value of 0.200 inches. We now proceed to configuration 2 of 2. The DHT parameter is the height of the bottom reinforcement. We will set a value of 0.093 inches. The next parameter, melt D, is the weld penetration depth. For this example, we will set a value of 0.050 inches. Finally, we configure the G distance, which corresponds to the heat-affected zone, HAZ. We will set a value of 0.200 inches. Once these values have been completed, we press the Finish key and assign a name to the scan plan. Confirming by pressing the OK key. Now we must select the scan plan we have created and confirm by pressing the Next key. For the next step, we will configure the transducer and the wedge. We verify that the probe selection parameter is set to Auto, and under wedge selection, we select the wedge being used. We also define the reference position where the transducer will be placed on the component, either left or right. The instrument offers two main modes: PE, pulse per element, which provides greater control and higher resolution, but results in a slower scan. PC, pulse per channel, which is faster and provides higher energy but with lower fine resolution. We select the mode according to the inspection requirements. It is also possible to change the transducer viewing mode: top view, front view, or side view, which we will use for this example. We press Next and adjust the following parameters: inspection range, which we set to 8 inches. Scan type sectorial. Wave mode shear. And verify the material velocity. We press Next again and configure the angular aperture. Start angle, 40 degrees. End angle, 70 degrees. Step 1 degree. Active elements, 1 through 16. If focalization is required, it can be calculated as the material thickness multiplied by 1.5. Otherwise, it is not necessary to activate this function. Finally, we have the ET distance, which is measured from the center of the weld to the front of the wedge and will be configured later. With this, we conclude the scan plan configuration. Velocity adjustment. First, we enter the main menu and select the velocity calibration option. Within this configuration, we will add two references, reference 1 and reference 2. For the first reference, we will use the radius of the calibration block equivalent to 100 millimeters, and for the second reference, the rebound from the same radius, with a total travel distance of 200 millimeters. In the gate mode option, we select sound path. Recall that depth mode measures only the vertical depth, while sound path measures the entire actual travel path of the ultrasonic beam within the material, which is essential when using angled beams in phased array inspections. We now adjust the gate and the range so that we can observe the two indications corresponding to the selected references. In this case, we will use a range of 250 millimeters. We set the gate height to 25% and the gate start to 100 millimeters. And a gate width of 150 millimeters. Now we place the transducer on the block and search for the maximum amplitude of both references. We move the gate to the first reference and, if necessary, adjust the gain to reach a reference level of 80%. It is now time to record our first reference, which corresponds to a distance of 100 millimeters, by pressing the record button. Now we move the gate to the second reference, which has a value of 200 millimeters, and increase the gain so that the gate intercepts this indication, then press record again. Finally, we press the Calculate option to apply the configuration to all elements and select Finish to complete the velocity adjustment. The instrument will automatically display a prompt to proceed with the next configuration. Delay adjustment. We enter the value of the reference block to be used. It is recommended to work with a reference greater than 25 millimeters to avoid near-field effects that occur at shallower depths. In this case, we will use a value of 100 millimeters. During velocity calibration, the instrument displays a parameter called reference error, expressed as a percentage. This value is not calculated by the operator. It is defined as a tolerance. It tells the instrument what level of error is acceptable before generating a warning. For example, if your instrument has the reference error limit option set to a value of 1.0%, you are defining that 1.0% as the tolerance. Then, when calibration is performed, the instrument calculates the actual error, for example 0.7%. Since this value is below the limit, the instrument accepts the calibration. However, if the error were 1.5%, the instrument would display an alert indicating that the established tolerance has been exceeded. For this example, we will use a range of 150 millimeters. We verify the parameters we have just adjusted and press the next key. We now position the gate to intercept the radius reference on the block corresponding to 100 millimeters. If necessary, we adjust the gain to achieve a reference level of 80%. By performing radial movements with the transducer, we ensure that all elements are within the reference level. Once the alignment of the elements has been verified, we press the calibration key. We verify again the start and end angles being used. For this example, we have a start angle of 40 degrees and an end angle of 70 degrees. We return to menu 1 of 2 and press the Finish key. The instrument will display a message confirming that the calibration has been completed and that we can proceed with the next adjustment. As an additional reminder, delay standardization ensures that all array elements transmit and receive in synchronization, eliminating time differences that would affect ultrasonic beam focusing. Finally, we confirm the adjustments we have made in order to proceed with the sensitivity adjustment. It is now time to perform the sensitivity adjustment. In the Gate Mode menu, we select the depth function. Here we find two parameters: the amplitude reference set to 80% and the error reference, which we set to 5%. According to the distance to be used for the sensitivity adjustment, we will use a known side-drilled hole with a diameter of 1/16 of an inch, equivalent to 1.6 millimeters, at a depth of 5 millimeters. We press the next key and apply couplant to the mini-PAX block, directing the ultrasonic beam toward the reference side-drilled hole. We perform slow forward and backward movements, ensuring that all sweep angles detect the reflector. At this point, we increase or decrease the gain as needed to reach the 80% reference level. Once we identify the echo from the side-drilled hole, we slide the transducer back and forth so that the green envelope is within the reference level. When the envelope is at the reference level, we press the calibration key. If necessary, we verify again that the calibration and sensitivity adjustment are within the reference level and press the calibration key again. The instrument will automatically adjust the decibels required to compensate sensitivity at each angle. We repeat this process until all crystals are within the reference value. Finally, we press the Finish key to conclude the calibration. To adjust the automatic gain compensation, we will use 3 reference points with known depths. First point, 5 millimeters, 0.200 inches. Second point, 10 millimeters, 0.400 inches. Third point, 15 millimeters, 0.600 inches. The values to verify will be amplitude reference at 80% and error reference at 5%. In the Gate Mode option, we choose depth and verify that the selected curve type is TCG. Now we press Next. We place the transducer on the mini-PAX block and direct it toward the side-drilled hole at a depth of 5 millimeters. If necessary, we adjust the range. It is recommended to adjust the gate so that it intercepts only the hole with the previously configured angles. We now slightly move the transducer back and forth until the green envelope echo from the side-drilled hole falls within the tolerances, represented by the yellow dashed lines. Once the adjustment is ensured, we press the record key. If necessary, we repeat this step until we confirm that we are within the established tolerances. Next, we press Next point to continue with the second point. For the second point, we recommend adjusting the range to 50 millimeters. We direct the transducer toward the side-drilled hole at a depth of 10 millimeters and adjust the gate. We verify that the gate start is positioned at the lower angles. We set the gate end at the higher angles. We again direct the beam toward the side-drilled hole at a depth of 10 millimeters and move the transducer back and forth, ensuring that the green envelope echo is within the reference range. We press the record key and once again move the transducer back and forth. We press the record key and once again move the transducer back and forth. We press the record key again. This process must be repeated until the green envelope is within the reference. Finally, we verify once again that it is within the tolerance range. We record the reference point again. In the same manner, we will generate the curve using the third point at a depth of 15 millimeters. To conclude the third point, we direct the transducer toward the side-drilled hole at a depth of 15 millimeters. We adjust the range to a value of 60 millimeters and begin moving the transducer back and forth so that the envelope once again reaches the tolerance limits. We press the record key and again perform back and forth movements, seeking the reference levels as in the previous points. To finish, we press the next key twice. From this point on, we can create additional curves. For this example, we will create two curves. The reference level is set at 80% amplitude. The second curve will be plotted at -6 decibels, and the third curve at -14 decibels relative to the reference level. We press the Finish key to complete the configuration. We have completed the standardization of velocity, sensitivity, delay, and TCG of the SyncScan 2 flaw detector. On the main screen, we can observe that the TCG curve has been correctly activated, along with the additional curves generated during the adjustment. Now, to review the configured profile, we enter the Basic menu and select the Display option. We then select the INDN function. Within this section, we enable the Group Display and Focus functions. The HT display function allows us to visualize the profile with and without reinforcement. After completing these adjustments, we enter the Display menu and select the Measurement option to add the ER distance value. For this example, we consider a distance where the weld profile lies within both the minimum and maximum angles of the sectorial scan, which corresponds to the distance between the front of the wedge and the center of the weld. Once this is done, we exit the menu and access the Scan menu, where, if necessary, we adjust the range to the value defined for the inspection. We've concluded the adjustments and standardization of the SyncScan 2 instrument.